Imagine the following philosophical reflection: if a tree falls in a forest with no one around to hear it, does it make a sound? A quantum physicist might say the sound was there, but the tree is less certain. This paradox takes us directly to the heart of quantum mechanics, which challenges our traditional understanding of reality. Quantum mechanics suggests that particles exist in a state of probability until they are observed. This phenomenon is known as quantum superposition, where particles like electrons and photons can be in multiple states at once. This concept may seem abstract, but it has profound implications. In quantum mechanics, the observation of a phenomenon not only records reality but helps define it. Without an observer, a particle can exist in various states simultaneously, but when measured, it collapses into a single state. This means that the very presence of the observer is crucial in determining the state of particles, introducing an intrinsic relationship between consciousness and physical reality. This paradox is not limited to subatomic particles. It raises philosophical and scientific questions about the nature of the universe as a whole. If the universe only assumes a defined state when observed, what does this mean for the reality we perceive? Are we only seeing a fraction of the true nature of the cosmos, shaped by our own observation? Quantum physics presents many challenges to our intuitive understanding of the universe, and Heisenberg's uncertainty principle is one of the most fundamental. Proposed by Werner Heisenberg in the 1920s, this principle states that it is impossible to determine both the exact position and momentum of a particle simultaneously. The more precisely we measure one of these properties, the less precisely we can know the other. This uncertainty is not due to technological limitations but is an intrinsic feature of the quantum universe. Imagine trying to measure the position of an electron. Using light to observe it inevitably alters its position due to the impact of the light photons. This act of measurement disturbs the particle, making it impossible to determine both its position and momentum accurately at the same time. This principle reveals that, at the quantum level, reality is indeterminate and probabilistic. Particles do not have defined positions and moments until they are measured, existing in a state of uncertainty. This intrinsic uncertainty has profound implications for our understanding of the universe. It suggests that the universe is essentially non-deterministic and governed by probabilities. This challenges the classical view of a universe where everything can be predicted if we have enough information. Heisenberg's uncertainty shows us that there are fundamental limits to what we can know, leading us to consider the existence of hidden variables that could, in theory, make the universe more deterministic. The idea of hidden variables arises as an attempt to explain the seemingly random and probabilistic behavior of quantum particles. According to this theory, there are unknown factors that determine the behavior of particles, but they are beyond our current measurement capabilities. If these hidden variables exist, they could provide a more complete and deterministic explanation of the universe, aligning quantum mechanics with the classical view of physics. One of the main proponents of the hidden variables theory was Albert Einstein. He believed that quantum mechanics was incomplete and that a more fundamental theory, including these variables, could explain the inherent uncertainty and probability in quantum theory. Einstein famously said, "God does not play dice with the universe," expressing his conviction that particle behavior must be determined by underlying factors that we do not yet understand. However, so far, no concrete evidence has been found to support the existence of these hidden variables. Experiments like Bell's test have shown that if hidden variables exist, they must obey very specific rules that differ radically from classical expectations. These tests have demonstrated that quantum mechanics, with its indeterminacy and probability, offers a more accurate description of subatomic phenomena than any hidden variable theory tested so far. Following this line, John Wheeler's experiments are among the most intriguing in quantum physics, highlighting the peculiar nature of particle behavior. Wheeler proposed a series of experiments known as delayed choice experiments to explore how photons and other quantum particles behave as waves or particles depending on the experimental setup. These experiments suggest that the decision to measure a particle as a wave or particle can be made after the particle has already passed through the interferometer, challenging the traditional notion of causality. Imagine a photon is sent through an interferometer, a device that can measure whether the photon behaves as a wave or a particle. If the choice to measure as a wave or particle is made after the photon has already passed through the interferometer, the photon still chooses the correct behavior according to the final setup. This suggests that quantum reality is not determined until the measurement is made, raising the possibility that particle behavior is influenced retroactively by how we choose to measure it. These results are deeply counterintuitive and challenge our classical understanding of cause and effect. They suggest that the act of observation plays a crucial role in defining quantum reality. Quantum particles seem to know how to behave based on the experimental setups, even if these setups are decided after the particle has passed through the experiment. This quantum strangeness leads us to consider the various interpretations of quantum mechanics, each offering a different perspective on uncertainty and the nature of reality. Quantum mechanics, with its precise predictions and confirmatory experiments, is undeniably successful. However, interpreting what these results really mean for the nature of reality has been the subject of intense debate. There are several interpretations of quantum mechanics, each offering a different view on quantum uncertainty and the nature of the universe. The Copenhagen interpretation, proposed by Niels Bohr and Werner Heisenberg, is one of the most well-known. According to this interpretation, a quantum particle does not have a defined position or momentum until it is observed. Before measurement, the particle exists in a superposition of possible states. The wave function, which describes this superposition, collapses into a single state when the particle is measured. This view places observation at the center of quantum behavior, suggesting that reality is defined by the act of measurement. Another fascinating interpretation is the many worlds theory, proposed by Hugh Everett III. According to this interpretation, all possible outcomes of a quantum measurement actually occur but in distinct parallel universes. When a particle is measured, the universe splits into multiple universes, each reflecting one of the possible outcomes. This eliminates the need for wave function collapse but implies the existence of an infinite number of parallel universes. Another interpretation is Bohmian mechanics, or pilot wave theory, which offers a deterministic approach to quantum mechanics. According to this theory, particles have defined positions and moments but are guided by a pilot wave that determines their behavior. This interpretation reintroduces an element of determinism into quantum mechanics but is less popular due to its complexity and lack of direct experimental evidence. Each of these interpretations tries to answer the same fundamental questions about quantum uncertainty and the nature of reality. While none have been universally accepted, all contribute to our understanding of the strange and mysterious properties of the quantum universe. With this, we come to the most accepted theory about the origin of the universe, the Big Bang, suggesting that everything began from an extremely hot and dense state and expanded over time. There are several lines of evidence supporting this theory, each contributing to our understanding of the history and evolution of the cosmos. One of the most convincing pieces of evidence is the expansion of the universe, discovered by Edwin Hubble in the 1920s. Hubble observed that galaxies are moving away from each other, implying that the universe is expanding. This suggests that if we go back in time, the universe would have been much smaller and denser. Another crucial piece of evidence is the cosmic microwave background radiation, discovered in 1965 by Arno Penzias and Robert Wilson. This radiation is the leftover heat from the Big Bang, present throughout the universe. It is a kind of echo of the initial moment, providing a direct glimpse into the primordial state of the universe. The uniformity of this radiation in all directions is a strong indication that the universe began from a hot, dense state and expanded uniformly. The distribution of light elements like hydrogen, helium, and lithium also supports the Big Bang theory. The proportions of these elements observed in the universe match the predictions made by Big Bang models. During the first few minutes after the Big Bang, conditions were ideal for nuclear fusion, resulting in the formation of these elements. Modern observations of the abundance of hydrogen and helium are consistent with theoretical expectations, providing another robust line of evidence. These combined pieces of evidence form a coherent and compelling picture of the origin and evolution of the universe. They help us understand how the universe expanded and evolved over billions of years, leading to the formation of the cosmic structures we observe today. With this arises the next piece of the puzzle, the theory of cosmic inflation, which explains the uniformity of the universe and other observed features. The theory of cosmic inflation is a crucial extension of the Big Bang model, propose to explain some intriguing features of the observable universe. According to this theory, the universe underwent a period of extremely rapid and exponential expansion in the first moments after the Big Bang. This phase of inflation would have occurred in a fraction of a second, but its consequences are evident in the uniformity and structure of the cosmos. One of the main motivations for cosmic inflation is the uniformity of the previously mentioned cosmic microwave background radiation. Without inflation, it is difficult to explain why regions of the universe that are very far apart have the same temperature and density. Inflation suggests that these regions were very close in the past before being rapidly separated by the inflationary expansion. This explains why the universe appears so homogeneous and isotropic on large scales. Besides solving the uniformity problem, cosmic inflation also explains the absence of magnetic monopoles and the flat geometry of the universe. During inflation, any initial curvature of space would be diluted, resulting in a universe that appears to be geometrically flat. This is consistent with modern observations, which indicate that the universe has a critical density very close to the value required to be flat. Cosmic inflation also makes testable predictions that have been confirmed by observations. For example, the small fluctuations in the density of the cosmic microwave background radiation, which are the seeds for the formation of galaxies and other cosmic structures, were predicted by the inflation theory. These fluctuations have been observed and mapped in detail by satellites like COBE, WMAP, and Planck, providing strong support for the inflationary theory. These achievements make cosmic inflation a fundamental part of our modern understanding of the universe. The theory not only resolves several important questions left by the Big Bang model but also opens the door to the idea of a multiverse. According to this theory, inflation did not occur just once but continues to occur in different regions of space, creating multiple bubble universes. Each of these bubble universes can have its own physical laws, fundamental constants, and initial conditions, forming a vast multiverse of parallel universes. The idea of the multiverse arises naturally from quantum mechanics applied to inflationary cosmology. During inflation, quantum fluctuations can cause variations in the expansion rate in different regions, leading to the creation of new bubble universes. These bubbles expand and separate, each following its own evolutionary path. Our observable universe would be just one of these bubbles, a small part of a much larger ensemble. This conception of the multiverse has profound philosophical and scientific implications. If there are multiple universes, each with its own properties, it can explain why our universe has the characteristics necessary for life. In a multiverse, all possible combinations of physical laws and fundamental constants exist somewhere, so it is not surprising that at least one of these universes, ours, is suitable for life. This idea, known as the anthropic principle, suggests that we observe a universe compatible with life because otherwise, we would not be here to observe it. Furthermore, the concept of the multiverse challenges our understanding of reality and existence. It raises questions about the nature of observation and measurement, as well as about the interconnectedness between these universes. Cosmic inflation and the multiverse also make testable predictions, such as the possible detection of signs of collisions between bubble universes, which could leave observable marks in the cosmic microwave background. These fluctuations have been observed in detail by satellites, which have mapped the cosmic microwave background with high precision, confirming the existence and magnitude of the fluctuations predicted by inflation. The analysis of these data showed that the fluctuations are consistent with a universe that underwent a phase of rapid and uniform expansion, solidifying the position of cosmic inflation as a valid explanation for the initial conditions of the universe. Another important prediction of the inflation theory is the flat geometry of the universe. Inflation would have expanded any initial curvature of space, resulting in a universe that appears to be geometrically flat. Modern measurements of the density of matter and energy in the universe, as well as the analysis of the cosmic microwave background, indicate that the universe is indeed very close to the critical density required to be flat. Furthermore, cosmic inflation predicts the existence of primordial gravitational waves, which would be generated by quantum fluctuations in the gravitational field during inflation. These gravitational waves would leave a specific signature in the polarization of the cosmic microwave background. The search for this signature is ongoing, and the detection of these gravitational waves would be a decisive confirmation of the inflationary theory. These observations provide strong support for the theory of cosmic inflation but also raise new questions and challenges. All this leads us to the intriguing observer paradox. It suggests that the act of observation not only records reality but also defines it. At the quantum level, observing a phenomenon causes the wave function to collapse, determining the final state of the observed particle. This implies that reality, in a sense, depends on observation, leading to profound questions about the nature of existence and the role of the observer in the universe. In the context of the multiverse, the observer paradox takes on a new dimension. If there are multiple universes, each with its own realities, the question is, what is the role of the observer in each of these universes? The anthropic principle suggests that we observe a universe compatible with life because we are here to observe it. This means that simply observing a specific universe can influence the reality of that universe. In other words, our existence and our observations may be intertwined in ways we do not yet fully understand. Quantum mechanics suggests that observation is not a passive act but an active process that involves interaction between the observer and the observed phenomenon. This process raises the possibility that different observers in different universes may experience distinct realities, each shaped by their own observations. This concept challenges the traditional view of a single objective reality and suggests that reality may be more subjective and observation-dependent than we imagined. The idea that our observations shape quantum reality also raises questions about the nature of time and space. If the universe is indeed a multiverse of parallel realities, then the time and space we experience may be just one facet of a much more complex and interconnected reality. Exploring these ideas leads us to consider the intersection between science and philosophy and to seek new ways of understanding the nature of existence. This discussion about the observer paradox leads us to a point of reflection on how science and philosophy intertwine to explore the mysteries of the cosmos. Exploring the theory of the hidden universe and the scientific discoveries that support it leads us to a deeper and more complex understanding of reality. From the initial philosophical reflection to quantum paradoxes and Big Bang evidence, we have seen how each piece of this puzzle brings us closer to a more comprehensive view of the cosmos. The various interpretations of quantum mechanics, from the Copenhagen interpretation to the many worlds theory, show us that reality may be much more fluid and subjective than we imagined. Discoveries about cosmic inflation and the multiverse open new possibilities for understanding how the universe evolved and how it may be just one of many. And the observer paradox reminds us that our observations not only record but also define quantum reality. If this journey through the mysteries of the universe and reality has piqued your curiosity, don't forget to subscribe to the channel and turn on notifications. Keep following our videos to explore more about the incredible secrets of the cosmos and the discoveries that can transform our understanding of everything. Until next time.